Okay, this is the answer key to the part 1 of the waves video. Okay, number 1, it says a pendulum completes 30 cycles in 15 seconds. Calculate the frequency. So frequency from the previous formulas is basically the number of cycles per overall time, total time, right? And that's going to be 30 cycles in 15 seconds. So it's a frequency of 2 cycles per second, or 2 hertz. Okay. What is the period of the pendulum that has a frequency of 10 hertz? Well, we know the period is the reciprocal of frequency, and frequency is the reciprocal of period. So this is just going to be 1/10 of a second. A child swings. Child on a swing completes 20 cycles in 25 seconds. Find the frequency. So the frequency, just like up here, it's going to be 20 cycles in 25 seconds. So that's going to be 0.8, it looks like. 0.8 hertz. So they do 0.8 of a cycle in 1 second. Okay, and the period is just the flip of that, or 25 divided by 20, which is 1 1/4. The Sears building in number 4, the Sears building in Chicago sways back and forth at a vibration frequency of 0.1 hertz. What is the period of frequency? Just take the 0.1 and flip it. So that's just going to be 10 seconds. So in 10 seconds, it completes 1 cycle. Okay, for number 5. If a water wave vibrates up and down 2 times each second, so that's your frequency basically. So it does 2 cycles per second. And the distance between wave crests is 1.5 meters, so that's your wavelength. What is the frequency of the wave? So that's 2 hertz. And what is the wavelength? We already said that it's 1.5 meters. And the speed of the wave is frequency times wavelength. So that's going to be 2 times 1.5. So that's 3 meters per second. This should be pretty straightforward, this stuff here. What is the wavelength of a 340 hertz? So that's frequency. Wave when the speed is 340 meters per second. So speed is lambda times frequency. You have the V, you have the frequency, you can just divide and find the lambda. The wavelength of a water wave is 0.08 meters. So basically the distance crest to crest is that much, so that's lambda. If the frequency is 2.5 hertz, what is the speed? V equals lambda times frequency again. Okay. A source with a frequency of 20 hertz produces, so frequency produces water waves that have a wavelength of 3 centimeters. So you have to be careful here with the 3 centimeters. Unless if you want to find your speed in centimeters per second, you can do that. So speed is lambda times frequency. So if you want to leave that in as 3 centimeters, your speed will be 60 centimeters per second, or 0.6 meters per second. Number 9, a wave in a rope travels at a speed of 2.5 meters per second. If the wavelength is 1.3 meters, what is the period of the wave? So this is your lambda, this is your speed, looking for the period. So I'm just going to use this formula. V equals lambda over period. So this is 2.5 equals 1.3 over t. So t is 1.3 divided by 2.5. An FM station broadcasts radio signals with a frequency of 92.6 megahertz. So mega is a million, so this is 92.6. So your frequency is 92.6 times 10 to the 6th hertz. Gotta change that. Okay. If the radio waves travel at a speed of 3 times 10 to the 8 meters per second, so all electromagnetic waves travel at that speed. That's the speed of flight also. What is wavelength? So V equals lambda times frequency. So 3 times 10 to the 8 equals, we're looking for that lambda. We have the 92.6 times 10 to the 6th. And you can just divide, and you should get 3.24 meters. Okay, number 11. Two waves have the same period. What other properties of these two waves must also be the same for each? Well, if they have the same period, they have to have the same frequency, because frequency is 1 over period. So the answer is C. The diagram above, number 11-1. The diagram above represents a transverse wave on a rope with point A labeled as shown. On the diagram, mark an X at a point on the wave that is in phase. In phase means like it looks similar. Okay, so if I have to do it, it will be this point here. Okay, so that's what in phase means. In other words, the difference between them is a multiple of a whole wave, or a whole cycle, or a wavelength. So other ones could be this one, okay, with this one. See, this is coming down, this is coming down. Those two are in phase. If you're looking for things that are out of phase, meaning like a difference between them is half a period or half a cycle, you got those two right there, okay? Or you can have these two right there. Okay. Now let's look at this RT1. So the grids are identical. Okay, the waves all have the same speed, but their amplitude and wavelength may vary. Rank the frequency. Okay, so frequency is speed over the wavelength. Okay, now the speed is the same, so which means that frequency is inversely proportional to the wavelength. So it looks like the one with the greatest frequency is going to have the shortest wavelength. So it looks like it's going to be B first, then it's going to be A, then C and D will come last. Okay, and actually you can just look at it here, and you can see that B has to come first because these waves in B are happening more frequently. That's pretty much what frequency means. Okay, and here these are happening less frequently than B, and C and D are the worst because there are not a lot of waves happening over the same period of time. Okay, we're going to look at number 12. Okay, a piano wire of linear density, a mass density of that 0.005 kilograms per meter is under tension of 1350 newtons. What is the wave speed in this wire? So I gave you another formula for speed in a rope, in a string. It's going to be the tension. T is the tension here, not the period, over the mu, which is the linear mass density, equals 1350 divided by 0.005. And make sure you take the radical of that. The answer should be 519.62 meters per second. Which of the curves shown in the figure best represents the variation of the wave speed as a function of tension? So now we know that V is proportional to the square root of the tension. Okay, so the only graph that shows a square root function is B. Okay, let's look at RT2. Okay, so we say that in the previous video that if the end is loose, meaning this ring can go up and down freely, this pulse will come back the same way in the same direction it was sent. And the reason for that is, if this were fixed, when this comes here, it pushes down on the rod, and the rod will push up on it and reverse it. But here we don't have that problem. Okay, so here when it's coming, this moves. It doesn't. The string doesn't just push down on it. This actually moves with it. So that's why it comes back the same way. That's all Newton's third law, basically. Okay. Two pulses travel towards each other along a long stretch spring as shown. Pulse A is wider than pulse B, okay, but not as high. Is the speed of pulse A larger, smaller, or equal to that of B? Now, if two pulses are traveling in the same medium, okay, the speed is the same. So the speed only depends on the medium and the conditions of the medium. So in other words, if you have a rope that's got a certain amount of tension, you will have a certain speed. If you change the tension, you will have a higher speed if you increase the tension. Okay? But for the same tension here, which is true here because you can have a different tension at location A than at location B. So for this string, the speed will be the same because the speed is medium dependent. Okay, 14. A speaker is connected to a wave generator producing sound waves of frequency 250 hertz. Which of the following will increase the amplitude? Okay, so the amplitude has to do with how much energy. So if I have, is stored in a wave. So if I have a wave that looks like that, compared to a wave that looks like this, the bottom one has more energy stored in it because it has a higher amplitude. Okay, so in order to increase the amplitude, it was just to have to change the volume higher. Let's look at 15 and 16. The diagram above represents a wave traveling to the right through a material. The frequency is 2 hertz. What is the speed? Now, if you look at this picture here, in here you have one wave here and another half. So if you want to figure out the wavelength, you take this whole distance and you divide it by the number of waves. So you have a wave and a half. So this should be just 4 meters. So that's your wavelength. Okay, so to find the speed, you just do wavelength times frequency. So that should be 8 meters per second. So the answer is C. Okay. The wave now travels into a new material in which the wave speed is faster. Now, the frequency is going to be the same. That's not going to change, right? Because the frequency has nothing to do with the medium, with the material. It's basically generated by something through that medium. So the frequency is 2 hertz. Okay. Speed went up. Okay, so what's going to happen to the wavelength? So V is lambda times frequency, right? If this frequency is constant, if the V goes up, the lambda has to go up. So it should be longer. Okay. We talked about this in phase concept. So the ones that are going to be in phase, it looks like C and G are in phase, but that's not a choice. So let's say if A and D are in phase. A and D are definitely not in phase. Okay, they're actually 90 degrees out of phase. A and G are not in phase. This one is going up, this one is coming down. C and K, C is coming down, K is coming down. That's in phase, right? And between them there is There are 2 cycles between them, exactly 2 cycles. So those are in phase. So when there is a whole number of cycles between the points, they are in phase. When there is an odd number of cycles, then they are out of phase. Or actually, when there is like a, not an odd number, when it's like multiples of half a cycle. Yeah, an odd multiples of half a cycle, basically. All right, number 18. If the frequency of a violin string is to be increased by 20%, what change in tension must be applied? So V equals F, or tension, basically, over that linear density mu, right? With the square root. Now V is also lambda times frequency, right? So if you want to change the frequency, increase it by 20%, okay, so this is going to become, the frequency will not be frequency, it will be 1.2 times the frequency, equals, now the question is, what do we put inside here that will come out as 1.2? And I think the answer is, we have to put in 1.44. Yeah. Okay, if you put in a 1.44, if you take the square root of 1.44, you should get 1.2. Oops. Yeah. Which means the tension has to increase by 44%. Okay, number 19. A string of mass m is under tension, and the speed of a wave in the string is v. What would be the speed of a wave in the string if the mass of the string is increased to 2m, but no change in the length of the tension, in the length or tension? So if the length is not changed, the lambda will remain constant, tension will remain constant. So v equals square root of tension over the mu here, right? So if you double this mass, this will double. So if you put a 2 here, you have to put a 2 here with the radical, because this is under the radical. So the answer should be B. Okay. Number 20. In an experiment, waves that all have the same wavelength are created in different materials. The speed of the wave is measured as a function of time, of the period. Okay. Which of the following represents a correct graph of wave versus period? Well, V equals lambda times period. The wavelength is the same. It's telling us that up here. So this is an inverse relationship. So the answer should be A. And that should do it for this video. All right.